Hello and welcome. Today, we're diving into something that powers, well, pretty much everything you use, the electric current and cells. So let's get right into it. So have you ever actually thought about this? I mean, your phone needs electricity. The wall socket has electricity, so what's the problem? Well, stick with me, because by the end of this, you'll know exactly why that would be a very, very bad idea for your phone. Okay, so to understand the crazy amount of power coming from our walls, we first need to get a handle on how it moves. And for electricity, that journey always happens inside something we call an electric circuit. Think about building the simplest circuit imaginable. You just need four key things. First up, you need a power source, right? Something like a battery. Second, you need a path for that power to travel, and that's where the wires come in. Third, you've got to have a controller, like a switch, so you can turn it on and off. And finally, you need the load. That's just the thing you actually want to power, like this lamp here. When you flip that switch, the path is complete, and boom, the light turns on. Simple as that. And that flow we just created? That's what we call electric current. It's basically a stream of tiny charged particles moving through the wires. And this one idea, this flow, is what powers everything from a tiny flashlight to the biggest machines in a factory. But, and this is a big but, here's a crucial detail. That flow of electricity isn't always the same. Turns out there are actually two very different types of current, and you really need to understand both. So let's meet the two main characters in our story today. You've got direct current, or DC, and you've got alternating current, or AC. They're both electricity, for sure, but they work in fundamentally different ways. So where do we get these two types of current? Well, DC power, that typically comes from converting stored chemical energy. Like in a battery. AC power, on the other hand, comes from converting motion into electricity. Think about the huge spinning generators at a power plant, or even a small dynamo on a bicycle wheel. All right, so let's put them head to head. This is the showdown, because understanding the differences between DC and AC is really the key to understanding our entire modern electrical world. This chart really lays it all out. You see, DC from batteries, it's like a one-way street. It flows in one constant, steady direction. Now, that's perfect for small devices, but it just doesn't travel well over long distances. AC, from generators, is the total opposite. Its direction and its intensity are always changing, and that unique feature is exactly what allows it to travel hundreds of miles to power our homes and cities without losing all its energy. Let's really picture this. Direct current is a one-way street. It flows steadily and directly, always from the positive side of a battery to the negative side. It's simple, it's predictable, and it's constant. Now, alternating current is a whole different ballgame. It doesn't just flow, it oscillates. It moves back and forth, constantly reversing its direction. And this constant change, that's its secret sauce. It's what allows us to easily change its voltage and send it super efficiently over really long distances. Okay, now if you remember one thing, make it this. It is incredibly easy to take high voltage AC from the power grid and convert it into the low voltage DC our electronics need. That's exactly what your charger does. But trying to do the opposite, trying to efficiently boost DC voltage up for long distance travel is way harder. This is probably the single biggest reason our entire power grid is built on AC. Okay, so let's zoom back in on DC and our batteries, or what we call cells. What happens when you need more power than just one cell can give you? Well, you have to connect them, and there are two main ways to do it, in series or in parallel. First up, we've got a series connection. You're probably super familiar with this one, even if you don't know its name. It's what you do when you put batteries in a TV remote. You place them end to end, connecting the negative side of one to the positive side of the next, making a little chain. So, why do we connect them like this? Well, because in series, the voltages add up. You can think of voltage as kind of like electrical pressure. So if you connect three 1.5 volt batteries in a row, you get a total of 4.5 volts of pressure. You're basically creating a more powerful source. Now, the other method is called a parallel connection. For this, you line up the cells side by side. You connect all the positive ends together with one wire, and then you connect all the negative ends together with another wire. It looks totally different from a series connection. But hold on, what's the point if the voltage doesn't add up? If you connect those same three 1.5 volt batteries in parallel, you still only get 1.5 volts. So what gives? Well, the benefit here isn't more power, it's more endurance.
Think of it like having 3 fuel tanks instead of 1. The pressure's the same, but your supply is going to last much, much longer.
All right, let's bring it all home. Let's see how all of this, AC, DC, volts, and chargers, comes together to solve that puzzle we started with. So here's the situation. The socket in your wall is dishing out powerful, high-voltage, alternating current. But your phone's battery? It's delicate. It needs gentle, low-voltage, direct current to charge up safely. The two are completely incompatible. Pushing 220 volts of AC into a tiny device that only wants 5 volts of DC would instantly fry its circuits. Game over. And that, my friends, brings us to the hero of our story, your phone charger. That little block is so much more than just a plug. It's like a miniature power station doing 2 absolutely critical jobs. First, it uses something called a transformer to step down that high voltage to a safe level. Second, it converts the back and forth alternating current, the AC, into the steady one-way direct current, the DC, that your phone's battery can actually use. So let's do a super quick recap. Electric current is just the flow of charge. DC is that one-way street from batteries, perfect for our portable gadgets. AC is the back and forth current that powers our entire grid because it travels so well. And when you're connecting batteries, remember, series gives you more voltage, more power. All parallel gives you the same voltage, but for a longer time. And that brings me to a final question for you to think about. Your phone charger is not the only little transformer working behind the scenes in your house. So take a look around. What other electronics have one of those power bricks or a big chunky plug? Every single one of them is secretly managing that same showdown between AC and DC, all to power your world.